Dear students, welcome to EPG Pathshala. Today we are going to discuss on energy conversion using magnetic fields. In this module, we are going to learn about different conversion methods using magnetic field for the production of energy. The major one or the most important method is by the use of electric generator. In this device, the mechanical energy is converted to electrical energy. We will discuss what is electric generator, what are the classification of generator, electric generator based on the AC, alternate currents or the DC current, and further the subclassification of the alternate current generators, electric generators, and the DC electric generators. The other method is MHD, which means magnetic hydrodynamic system. In this, the kinetic energy of the material is placed in a magnetic field and it is converted into the electric energy. We will see what is the working principle of this MHD system, what are the different types of MHD system, MHD generator, and also what are the advantages and limitation of this MHD system. So let's start with magnetic field. Magnetism is a property of material, and the magnetic field produced by a magnet or a current carrying conductor is the space where the magnetic lines of force is experienced. Magnetic field is a vector unit which has both direction and a magnitude. The common laws in relation to magnetic field are Biot-Savart law, Ampere's law, and Faraday's law. Let's see Biot-Savart law. This states the relation between the magnetic field generated, which is denoted by the symbol B, to the magnetization force denoted by the symbol H, and the induced electric current, which is denoted by the symbol I at the conductor. Where you can see in this equation B is equal to nu 0 nu r H, and it is further integrated. Here the integral sums over the conductor length, where dl is the line vector element, nu 0 nu r are the magnetic constants, r is the distance between location of dl and the location where the magnetic field is calculated, and r cap is a unit vector in the direction of r. Ampere's law relates the electric current to the magnetic field in a modified form that accounts for time varying electric fields. In this equation, where the line integral is over any arbitrary loop and I enclosed is the current enclosed by the loop. This law is valid only for the steady currents and can be used to calculate the magnetic field for highly symmetric conditions. The relation between the induced voltage in a closed circuit and the rate of change of the magnetic flux it encloses was defined by the Faraday's law. Here, E is the induced voltage and negative sign is due to the direction of the induced electromotive force. Generating electric power in a wire loop can be achieved by varying magnetic field, varying the number of conductor loops, and by varying the intersecting area of the conductor loop. Let's see what is electric generator. These are rotating electric machines and converting mechanical energy to electricity using the laws of electromagnetism. The parts of electric generator are stator, which is a stationary member, rotor, which is a rotating member, shaft and bearing, slip ring, commutator or brush assembly, armature and field windings. There is an air gap between stator and rotor of the generator. In rotating field synchronous machines, the machine armature windings are placed on the stator and field windings placed on the rotor to provide a low reluctance path to the magnetic field produced at stator and rotor. Stator and rotor are made up of high-grade magnetic material such as silicon steel. In practice, a brush assembly or slip rings are required to take out the generated power from the rotor, which is the rotating member of the turbo alternator. In case of DC generators, a set of switches mounted on armature, which is called commutators, was used to convert the generated AC power to DC power. The ventilating ducts are also provided with machines for cooling purposes. For large turbo alternators, instead of air, hydrogen is used as a coolant. A closed-circuit ventilating system is preferred for large capacity machines. The hydrogen is circulated over the machine parts and is cooled with the help of water-cooled heat exchangers. An arrangement of the winding which is used as a primary source of flux when current is passed through it is known as field winding or exciting coil. In some application, permanent magnets are used to produce main flux. An arrangement of the conductors to form a winding in which EMF is induced is known as armature winding or armature coil. The current flowing through the field winding used to produce main flux is known as magnetizing current, exciting current or field current. The armature current varies as the load on the machine varies. So it is called load current or armature current. The current in the exciting winding is always DC current. Let's see the classification of electric generators. This classification is based on type of the output current. It's divided into two groups, alternating current generators or alternators and direct current generators. You can see in this flow diagram, electric generators are classified into AC generators and DC generators. Further, AC generators are divided into synchronous generators and asynchronous generator. Let's see the classification of alternators. Based on operating principles, alternators are classified as I told, synchronous and asynchronous generators. Asynchronous machine consists of a stationary armature winding, that is the stator, with conductors connected in series or parallel to obtain the desired terminal voltage. As the magnetic flux developed by the rotating DC pole crosses the air gap of the stator windings is as shown in the figure. A sinusoidal voltage is developed at the generator output terminals. This process is known as electromagnetic induction. The magnitude of the AC voltage generated is controlled by the amount of DC excitation current supplied to the field. The frequency F of the voltage developed by the generator depends on the synchronous speed, that is denoted by capital N, of the rotor and the number of field poles P. Then F is equal to Np by 120. Synchronous generators are used in power stations and reactive power compensation at grid stations. Asynchronous generators, these are also known as induction generators. They operate at the super-synchronous speed by mechanically turning their rotor faster than synchronous speed, giving negative slip. A regular AC asynchronous motor usually can be used as a generator without any internal modification. Induction generators are useful in application such as mini hydropower plants, wind turbines, or in reducing high pressure gas streams to lower pressure because they can recover energy with relatively simple controls. To operate, an induction generator must be excited with a leading voltage. This is usually done by connection to an electric grid, or sometimes they are self-excited by using phase correcting capacitors. The induction generator requires one additional item before it can produce power. The reactive power may be supplied by the capacitors or from the utility grid. Induction generators are inexpensive and simple machines. However, they offer little control over their output. The induction generator requires no separate DC excitation, like the synchronous generator. Coming to the classification of DC generator. These generators are usually classified on the basis of their field excitation method. They are classified into three broad categories: separately excited, permanent magnet DC generator, self-excited generator. In separately excited DC machines, the field winding is supplied from an independent external DC source. That means the field winding is electrically separated from the armature circuit. Separately excited DC generators are not commonly used because they are relatively expensive due to the requirement of an additional power source or circuitry. Permanent magnet DC generator. Basic configuration of a permanent magnet DC generator is similar to that of a normal DC generator. It works on the principle of any DC motor, that is, When a current carrying conductor is placed in a magnetic field, it experiences a force. The permanent magnet synchronous generators, that is PMSGs, have permanent magnetic poles. So, there is no external field excitation source is needed. These PMSGs are widely used in renewable energy applications such as wind turbine systems and can be used for ocean current turbines. Self-excited DC generator. In this type, the field coils are excited from the current produced by the armature coil. Initial EMF generation is due to the residual magnetism in field poles. The generated EMF causes a part of current to flow in the field coils, thus strengthening the field flux and thereby increasing EMF generation. Self-excited DC generators can further be divided into three types: series wound, shunt wound, compound wound. Field winding in series with armature winding comes under the series wound type. Therefore, in this type the field winding carries the load current. In shunt wound, the field winding is connected in parallel with the armature winding. Hence, full voltage is applied across the field winding. In the case of compound wound type, there are two sets of field winding. One is connected in series and the other in parallel with the armature winding. Further, these compound wound machines are divided into short shunt and long shunt. In short shunt, field winding is connected in parallel with only the armature winding. And in long shunt, field winding is connected in parallel with the combination of series. Coming to the other conversion method, that is magneto-hydrodynamic power conversion. Magneto-hydrodynamics (MHD) is a method in which kinetic energy of charged particles in a conducting material in the presence of a magnetic field is directly converted into electrical energy. You can see the word magneto-hydrodynamic is derived from three words: magneto, which means magnetic field, hydro means water, and dynamics mean movement. So in actual practice, the heat is used to provide energy for the motion of charge carriers in a conducting material, which can be obtained by burning of fossil fuels. This heat is converted to electrical energy. This field of study was initiated by Dr. Hans Alfvén, a Swedish scientist, for which he was awarded with Nobel Prize. Let's see what is the working principle of this system. When an electrical conductor is moved so as to cut lines of magnetic induction, the charged particles in the conductor experience a force in a direction mutually perpendicular to the applied B field, that means B is the magnetic field, and to the velocity of the conductor. This law is Lorentz force law, where F is equal to Q V into B. F is the force acting on the particle, Q is the charge of the particle, V is the velocity of the particle, and B is the magnetic field. The vector F is perpendicular to both V and B according to the right hand rule. As the negative charges tend to move in one direction and the positive charges in the opposite direction due to the induced electric field or motional EMF, and this phenomenon provides the basis for converting into electrical energy. This is shown or explained in the figure. The maximum power output per unit volume is given by Pmax per unit volume equals 1 by 4 sigma V squared B square, where sigma is conductivity. The complete set of magnetic hydrodynamic equations for a Newtonian constant property fluid flow includes Navier-Stokes equation of motion, equation of mass continuity, Maxwell's equation, and Ohm's law. Let's see in detail MHD generator, magneto-hydrodynamic generator. A magneto-hydrodynamic generator directly extracts electric power from moving hot gases through a magnetic field, and it's based upon Faraday's law of electromagnetic induction. This law states that energy is generated due to the movement of an electric conductor inside a magnetic field. The MHD generator does not have any rotating coils, unlike the conventional rotating electric machine. These generators were originally developed because the output of a plasma MHD generator is a flame well able to heat the boilers of a steam power plant. The conversion process in MHD was initially described by Michael Faraday in 1893. The first known attempt to develop a MHD generator was made at Westinghouse Research Laboratory, USA around 1938. The first MHD steam power plant U25 was put into operation was of 75 megawatt unit in USSR, of which 25 megawatt is generated by MHD. In the early 1970s, the solid fueled MHD power system Sakhalin was constructed by Russia. The Japanese program in the late 1980s concentrated on closed cycle MHD. In 1986, Professor Hugo Carl Messerle at the University of Sydney researched cold fueled MHD. Coming to MHD systems, it is the generation of electric power utilizing high temperature conducting plasma, which is stream of high temperature working fluid moving through an intense magnetic field. It converts the heat energy of fuel, that is thermal energy, directly into the electrical energy. The fuel burns in the presence of compressed air in the combustion chamber. During the combustion, seeding materials are added to increase the ionization, and this ionized gas is made to expand through a nozzle into the generator. Magnetic field, a current is generated and it can be extracted by placing electrodes in a suitable stream. The ionization can be produced by thermal or nuclear means. Materials such as potassium carbonate or cesium are often used in small amounts, typically about 1% of the total mass flow, to increase the ionization and improve the conductivity, particularly the combustion of gas plasma. 90% conductivity can be achieved, fairly low degree of ionization of only about 1%. The types of MHD systems. There are two types of MHD systems, open cycle and closed cycle. Let's see in detail open cycle MHD generator. The arrangement in the open cycle system is shown in the figure. In this system, oil or gasified coal is used as fuel. The fuel is burned in a combustor and hot gases around 2500 Kelvin temperature from combustor are then seeded, which helps in the ionization of gases and their better conductivity. The gases are passed through the nozzle where they are accelerated. The MHD generator is a divergent duct with external cooling and applied perpendicular magnetic field to the motion of gases. A number of electrode pairs are inserted in the duct to conduct the direct electric current generated in the converter to an external load. The direct current power is converted into AC power by means of an inverter. As the working fluid travels along the duct, its energy is used and converted into electricity. The temperature of gases continuously falls and ionization of gases also reduces. When the degree of ionization becomes insufficient, the gases have to be discharged off from the converter. At this stage, the temperature of gases is about 1900 Kelvin and 25 to 35% of heat energy of the gases has been converted into electrical energy in the converter. The gases are used in preheater to heat fresh air for combustion and waste heat boiler to generate steam. The steam generated is used in steam turbine with a directly coupled generator which converts 25 to 30% of the total heat into the electric power. The gases exiting the boiler are passed through a seeding material removal device before discharging to the atmosphere using a stack. The bottoming cycle, you can see in the figure, it consists of boiler, steam turbine, condenser and a pump. Closed cycle system. In the system, argon or helium gas is used as the carrier gas. The Brayton cycle is used for the heat conversion. The gas is compressed and heat is supplied using a heat exchanger, which is marked as 1 in the figure. The fuel is burned in a combustor. Gasified coal is used as the fuel and hot combustion gases supply heat to the carrier gas through the heat exchanger marked as number 2 in the figure. The combustion gases exciting the combustor after transferring heat to the carrier gas are passed through an air preheater to heat the supply air before entering the combustor. The combustion gases after exciting from preheater are discharged to atmosphere using a stack. As the combustion gases and carrier gas are operating separately, there is no problem of extracting the seeding material in the system compared to the earlier open cycle system. The hot argon gas is seeded with cesium and hot carrier gas is passed through the MHD converter at high speed with the help of a nozzle. The DC power generated by MHD converter is converted into AC power with the help of an inverter. The hot carrier gas exciting from the MHD converter is slowed down using a diffuser. The hot carrier gas is passed to a waste heat boiler or heat exchanger to generate steam. This steam is used for running the compressor to compress the carrier gas with the help of turbine and for driving the turbine, coupled with generator to generate electricity. The carrier gas is returned back to the primary heat exchanger after passing through the compressor. A closed cycle system can provide more useful power conversion at low temperature of about 1900 Kelvin compared to the 2500 Kelvin for open cycle system. The lower operating temperature in closed system allows a wider choice of materials to be used with the system. So in comparison, you can see that the working fluid after generating electrical energy is discharged to the atmosphere through a stack in the open cycle system. While in the closed cycle system, the working fluid is recycled to heat the sources. And the operation of MHD generator is done directly on combustion products in open cycle system, while helium or argon, that is cesium seeding, is used as the working fluid in closed cycle system. The temperature required in the open cycle system is 2300 to 2700 degrees Celsius, while closed cycle system requires only 530 to 1400 degrees Celsius. Open cycle is more developed compared to closed cycle one, though the most efficient one is closed cycle. If you see the efforts in India, the first pilot plant was set up by BARC, Baba Atomic Research Center in Tiruchirappalli, Tamil Nadu. A 5-year plan was signed in February 1975, which included 22 spheres of applied science and technology connected with MHD energy generation. What are the advantages of MHD generating system? It has higher efficiency of 50 to 60% that can be achieved by using a hybrid plant consisting of an MHD generating system and a thermal power plant. It has no moving parts. It can be started up quickly. Its output can be easily controlled by adjusting strength of magnetic field and speed of ionized gas. It is a source of pollution-free power. These are the advantages. Coming to limitation, the limitations of MHD generating system are it requires a very high temperature for ionization of gas. It needs special materials to be used in its equipment which can withstand high temperatures and thermal stresses. Its equipment has limited life due to high temperature and thermal stresses. Its output power is direct current. Suitable inverters are required to convert DC into AC. It requires power to maintain the magnetic field. It also requires cooling of electrodes. To summarize, we have seen different methods of energy conversion using magnetic field. We have seen different laws of electromagnetism like Biot-Savart law, Ampere's law, Faraday's law. We have studied about the electric generator. It's a device which converts mechanical energy into electrical energy. We have seen its classification into alternate current generators and direct current generators. Further, we classified this alternate current generator into synchronous and asynchronous, while DC generator was classified into separately excited permanent magnet generator, self-excited generators. We have seen different parts of electric generators also. Further, we have learned about MHD, that is magnetic hydrodynamic system. We have seen in this system the kinetic energy of charged particles in the conducting material in a magnetic field is directly converted to electrical energy. The working principle of this MHD system is, or we have seen that it's which law it is? It is Lorentz force law. We have seen different systems, different types of MHD systems like open cycle, closed cycle system. In open cycle system, the working fluid after the electric energy generation, it is released to the atmosphere. While in the closed system, it is reused for heating the sources. Then we have seen different advantages of this MHD system, like it is pollution free, no moving part is involved, and efficiency is around 50 to 60%. But it has some limitation, like it is costly and the output is DC, so you need an inverter to convert DC to AC. And the efforts have taken from Indian side to convert energy using magnetic fields. Thank you.